the data that we get can consist of marks on a piece of paper. We have the release point for the rubber band, and we have 1, 2, 3, 4 pullback positions at more or less equal spacing. We might pull back a centimeter at a time. We might even actually measure these with a meter stick. By whatever method we use, we then mark the positions at which the rail stopped. And we want to do this, of course, on a smooth surface, a uniform surface. We don't want to use a rubber mat or carpeting, for example. We want a smooth wooden or tile type surface. We might actually take several readings here at each point. So we might get something that looks like this. If we are sure that we've pulled the thing back the same each time, we're going to use the furthest distance. Not the average of the distances, but the furthest. Because sometimes we don't release the rail as smoothly as we'd like, and we interfere with its acceleration due to the rubber band. And the furthest distance is going to be the one probably where we released it most cleanly, and that's the one we're going to take. Again, as long as we're sure that we've released it from the right point each time. Well, having obtained that data, we can easily sketch a graph. It turns out that the data does indeed look something like what we've shown here. Okay, so if our pullbacks are 1, 2, 3, and 4 units, our first distance is pretty short compared with our fourth. Our second distance is more than twice as much as the first. If it was twice as much, it would lie along a straight line starting at the origin and going through the first. So it's going to be something like this, and then like this. And we don't even have room for the fourth point on this graph. We'd have to rescale the graph in order to get the fourth point on there. However, we can see that there's going to be a tendency for a curve that swings in the upward direction. And we'll analyze the reasons for this.